All right, yesterday we took a look at calculating acceleration using our acceleration equation. Today we're going to take a look at calculating free fall acceleration. This is the same acceleration equation we used yesterday, except for all of our objects are going to be in free fall, so they're accelerating at 9.8 meters per second squared here on Earth. It changes depending on where you're located. If you're in the moon, right, the moon's acceleration due to gravity is going to be different. I would encourage you to watch the videos that I posted on Canvas. So anyway, I took the equations from yesterday and we're going to write them with the variable with acceleration due to gravity substituted in for your acceleration here. So it's just going to be g is equal to your final velocity minus your initial velocity divided by time. Your final velocity is going to be equal to your initial velocity plus g times time instead of a. Right? It's just a specific type of acceleration. Time is going to be your final velocity minus your initial velocity divided by g. And then your initial velocity is going to be your final velocity minus g times t. One thing to note about g is that it is always negative. So when I have an object that's being thrown up, I have an initial velocity that is positive and a non-zero. It's got to start from somewhere. It's going to be slowing down because my velocity is working against my acceleration. My velocity has a positive direction and my acceleration is in negative direction. On the way down, my velocity will have a negative direction and my acceleration will still have a negative direction. At the highest point in a projectile, the velocity for one-dimensional projectile, which these are, our velocity at the height of our flight is going to be 0. So keep these things in mind as we're going through these problems. I'm going to do a few for you, just like I did yesterday. So we'll do the last two. Number 10 says a water balloon is dropped from a high window and struck a target 1.1 seconds later. So anything that's dropped, our initial velocity is going to be 0 meters per second. It's stationary before your hand releases it. The time that was given to us is 1.1 seconds. And if the balloon left the person's hand, shoot. My initial velocity is given to me as -5 meters per second. I don't like how this question is written. Normally, if you see the word dropped, it implies that there's no initial velocity. I guess it's being thrown. I should say thrown. Anyway, it's being thrown down, so it has a negative velocity. And what is the velocity on impact? So I'm looking for my final velocity. And my acceleration rate is g, and it's going to be -9.8 meters per second squared. So this will not be given to you in the word problem, but it is a variable that you can use to solve for your equation. So this question is asking us to solve for final velocity. So I'm going to use the equation for final velocity. And I have to be careful about my direction here today, especially. So my final velocity, since the object is falling in the downward direction, I know my final velocity is going to be negative. So my initial velocity was given as -5 plus my acceleration due to gravity, which is 9.8, times my time, which is 1.1. -9.8 times 1.1 gives me -10.78. When I add that to -5, I get -15.78. meters per second. This is my final velocity. And it makes sense it's speeding up because my direction of my velocity is in the same direction as my acceleration. So they're working together. All right, for number 9, it says, in a bizarre but harmless accident, Superman falls from the top of the Eiffel Tower. How fast was Superman traveling when he hit the ground? 7.8 seconds after falling. So this only gives us the time, which doesn't seem like it would be enough, but we know our acceleration is negative 9.8. And he fell from the top, so we can assume that his initial velocity is going to be 0. And his final velocity is what we're looking for, so we will actually use the same equation that we used for the other example. So he's moving down, so his velocity will be in the negative direction, and his acceleration is in the negative direction. So he's actually going to be increasing his speed. This is 0, so we can cancel it out of our equation. Our g is negative 9.8, and our time is 7.8 seconds. So my final velocity is going to be negative 76.44. It's weird to think about somebody with a negative velocity can be speeding up, but you can when you're in free fall.